An ESR 5G wireless. He's a PhD candidate at Linköping University, and he has been recruited quite early. I mean, after 1 year that we started this project, he's working on massive MIMO. He's our super active, he's a paper machine. So he got paper accepted to ICC in Paris, which is going to be actually held here in just 20 kilometers from here. And today I guess he will be presenting this paper, right? Yeah. The ICC paper.
Yeah, right.
Okay? Yeah. So you have 15 minutes and then we'll ask you some questions.
Yeah.
Okay?
Good afternoon everyone. My name is Trinh Van Chien from Linköping University. Today I would like to present my paper named Joy Pilot Second Design and Power Control for Macmin Finance in Uplink Massive MIMO. So my work is under the guidance of my supervisor Emil Polonson and Eric Larson. First, we consider a quite popular multi-cell massive MIMO system. We have a multi-cell in the network like this way, and the number of cells L cell, and each cell we have one base station with M antenna, and this base station will serve K user at the same time. This figure is for uplink and this one is for downlink. Even though the propagation channel changes over the time, and frequency, you see. However, we assume that network operate in the coherence block of tau C symbol here, and in each coherent block we have to use some symbol for pilot chaining. And therefore, we assume that the total number of symbol for pilot chaining is tau p, and to avoid pilot contamination, we should have a constraint tau p larger than or at least equal to the total number of users in the network. It means that K multiply L. However, it's impractical. Therefore, in practice, we normally we have this constraint tau p less than KL. It means that the network suffer from pilot contamination. If we define an autonomous basic phi includes tau p vectors, and we let the L2 norm of each vector equal to 1, and then we can construct pilot sequence in the network by combination of columns in the autonomous basic phi here. And our goals of this research, we want to optimize the user pilots to maximize the minimum rate in the network.
It's not moving. Thank you.
Do you have like something online to
Sorry about that. Now we start with the first related work. I mean, the name of the first related work is mean pilot power control only. It means that in I'm sorry, this slide is correct one. I mean, we start with the first prior work is pilot assignment only. It means that in this the prior works, they only focus on pilot assignment. It means that we fix the power for pilot second here, and we can construct the pilot second for cell else by this figure. It's a multiplication of power, the autonomous basic and the permutation matrix pi L here. What I mean, the main thing they want to only consider pilot second only is that I mean, selecting the best permutation matrix PL is the NP-hard problem. It means that it's combinatorial problem, and then I mean, it's a very high computational complexity. Therefore, the prior works, they only consider the case, the number of, I mean, the length of each pilot second only equal to k to reduce the computational cost. However, even though with the simple case here, we still need to search over k factorial power L minus 1 possibilities of the permutation matrix PL here. Therefore, it somehow explains why they only focus on pilot assignment and fix the power control. Another, I mean, opposite with the previous work, this work they only focus on pilot power control only. It means that they construct the pilots for cell L's by autonomous basic phi and the pilot matrix PL is the diagonal matrix. And each user, for example, user K in cell L have one pilot level. This one it seems to be, I mean, it's not continuous because we only consider the diagonal element of matrix P is a non-zero power level and as a path are zero. This work takes benefits of pilot power control. However, I mean, they assume very simple pilot assignments in the network. For example, they use orthogonal pilot second for this work, or they assume fixed pilot allocation for this work, even though they consider the network affected by pilot contamination. Therefore, I mean, one simple way to improve the pilot design is we combine both of the previous work together and then use our notation. We can construct the pilot design in the product of three matrix, the autonomous basic pies, the auto, and this one is the permutation matrix and the power matrix. I mean, to find the best way to, the best pilot sequence in this design, we need to try to first we need to try to search all possibilities of permutation matrix, and we also need to optimize the pilot power. Therefore, to find the way we do here is that we first try to construct a dictionary contain all possibilities for the permutation matrix pi L here, and given the permutation matrix, we try to optimize the pilot power to construct the dictionary. We define chi LK is the pilot assignment index for user K in cell L, and we can construct the pilot review set for each user in the network by defining this one. They are equal. It means that two users in the network use the same pilot sequence. And this work, of course, we need to do a brute force search for all pilot assignment matrix. This slide, this slide shows our proposed method. Basically, we assume that the pilot power now is continuous variable. It's not, it's not big risk like the previous work. Someone, only diagonal elements are non-zero and other y are zero. We assume that every element in the matrix PL here can may be different. Non-zero elements. Therefore, we can construct our proposed pilot sequence design like that way. And we see that by design this pilot sequence, we don't need the permutation matrix. And if we can optimize the pilot power matrix PL, therefore we can do both power control and pilot assignment at the same time. And this one, the previous work, they assume that all users in the same cell should use orthogonal pilots. It means that in the same cell they want to reduce the pilot contamination inside a cell. However, this pilot design take more advantage. We assume that we allow for non-orthogonal pilot even in the same cell. Our aim at minimizing the total coherent interference in the network. Therefore, now we move to uplink massive MIMO transmission. Some symbol in a coherent block. We use for pilot chaining. This one is a pilot sequence, and we use MMSE estimation to estimate the channel. And for uplink data, we assume that if we assume that the channel is a relay, and then we use maximum ratio transmission, maximum ratio detection. We can calculate all SNR value for all pilot designs. The most, now we go in more detail about some important pilot design. With the joint pilot assignment and pilot power control, we see that the SINR value here depend on the pilot's review set PLKA here. It means that to seeking the best SNR for user K in cell L, we have to do brute force search over the dictionary D we talked before. Therefore, this one is maybe impossible for the large scale network. With our proposed method, we can come up with SINR value by this equation. The important thing I would like to note here is that the permutation matrix doesn't occur on this expression. It means that we can do both optimal pilot power control and pilot location at the same time. Now we formulate the max-min fairness optimization problem by consider the power control. The pilot power, like optimization parameter here with the SINR constraint and the total transmit power, pilot power should be less than the maximum value. that, I mean, with our SINR constraint, this one is a signominal function. Therefore, I mean, somehow we cannot solve it because it's a non-convex optimization problem. Therefore, I mean, it's difficult to find. It's difficult to find the optimal solution. However, we can, by define the pilot power like continuous variable, we can claim about the, I mean, the existence of the global or the optimal solution, and we also can find a local optimum by using this inequality and use a successive approximation method to find the local optimal solution. For joint pilot assignment and pilot power control, we need to searching over the dictionary D here. However, for given given pilot assignment matrix A, we can see that this one is a geometric program. Therefore, I mean, if we do in brute force search, we can find globally optimal solution for this problem. It's important benchmark for comparison between our proposed method and this benchmark, because this benchmark we can see the globally optimal solution. Now we come with some setup for numerical results. We consider 4 cells in the network. The distance between in area 1 kilometer, and we assume that users are uniformly randomized in each cell. However, the distance between base station and user is not less than 35 meters, and we to consider the impact of pilot's design, we assume fixed data power, data simple power, and for pilot's constraint, we assume the maximum pilot is 200 milliwatt. We use the graph around to simulate the interference as boundary effects at boundary, and large scale fading combine path loss and shadow fading. We compare our proposed pilot design with the most simple and popular one is universal random pilot assignment. It means that they only work with pilot assignment and very simple methods. They assume each all user in the same cell use randomly choose the pilot orthogonal pilot sequence. For more advanced technique, they use they call smart pilot assignment. It means that rather than decide randomly pilot sequence in each cell, they assume they use some prior information. It's a mutual interference to assign the pilot. And another is a pilot power control with brute force search over the dictionary D. This figure shows the CDF mean spectral efficiency for the number of user K equal to the length of pilot sequence equal to 2. We see that the universal random pilot assignment gain the worst performance. The mass pilot assignment somehow better than universal random pilot assignment, and our proposed pilot design performance very close to the global optimum here. One problem is that because this one is very high computational complexity, we cannot we cannot consider this method when we increase the number of users in the network. Therefore, next figure we only consider proposed pilot design, smart pilot assignment, and universal random pilot assignments. We see that our proposed method still gain as the best performance. And the second one, the second observation, we see that when we increase the number of users in the network, the spectral efficiency reduce much. Next one, we increase the number of antenna for each base station from 100 to 900. We see that, if we have more antenna as base station, the proposed method have a much better performance. If we see M equal to 100 and M equal to 900, it means that the proposed method is work quite well for massive MIMO system. This one is some conclusion. In this work, we propose new pilot design for multi-cell massive MIMO. We treat the pilot signal like as continuous optimization variables. Therefore, we can combine pilot allocation and pilot power control in a unified framework, and we can derive the closed form expression for algebraic rate, for relay fading and maximum ratio combining. We see that our proposed method have much better performance than varied designs and very close to the globally optimal solution. Thank you. This is the last.
Questions, comments? Let's first try with Leonardo, okay, and then I go to the others. Do you have any questions, suggestions?
Yeah, well, the name is Trinh, right?
Yeah.
So first of all, there are too many slides. So 16 slides plus the title. I think the title is slide number 0. Right? So there are too many, because there are 17 and they are also very dense. You're not going to make this in time. For the if this is for an ICC presentation, you have to cut something.
Yes,
I'm afraid.
I realized the problem after listening.
Yeah.
And also
You have to cut something. Also, there is no outline slides at the beginning.
Yes.
So you just start it's a cold opening, which might work, well, it depends. Your presentation is very aimed at massive MIMO.
Yes.
So I expect those attending your presentation will either understand whole of it or they don't understand a thing, which might be good. But if you want to, it might be useful to add some introduction, like explanation that your contribution is about massive MIMO and why massive MIMO is relevant. I know it sounds cheesy, but for ICC, it's worth doing. This is not a symposium, a technical workshop on massive MIMO only.
Yeah.
There will be a lot of people who don't really know much about massive MIMO. So I would add, first and foremost, besides the entire thing, something about the idea of massive MIMO.
Yes, I totally agree with you. Yes, in first slide, I somehow try to explain something about massive MIMO. For example, in this figure, it shows the difference between the normal, the conventional MIMO system and massive MIMO. Is that massive MIMO we have a very dense antenna here.
Yeah,
maybe I will try to.
Yeah, for example, you never say that M must be very large.
Yeah.
So it must be say somewhere.
Yeah.
And also, on the one hand, I liked the fact that you try to give a graphical explanation. In most of the slides, you give the matrix structure with colors, and it's very nice, actually. But I would go only for that. It means to revolutionize everything, but if you go slides 4 to 10 or so, you have this structure where you have this one, for example. You have a matrix with colors on the right-hand corner, which is good and nice, and you explain that you just take elements on the diagonal, which is very interesting. But then you have a long explanation there, and you mostly refer to that. And that's more redundant because you have them only in the corner. It's so small, it looks like it doesn't even matter. But actually that's maybe easier to follow than the formulas. At least, I guess, if somebody from the audience understands the formula, then they read the paper and they know exactly the same thing. If you want to convince somebody in the audience that you did a good job there, you just put the matrix over there. Because the formulas are very nice and everything, but there are too many. And I think, I don't know, maybe it's because I'm not that into, it's not that I don't know a thing about massive MIMO, maybe Marco is more expert than me, but from my, I'm not an expert on massive MIMO, but I know what it is.
Yeah.
And I wasn't able to follow the entire formula. I mean, it was too much. After, well, 2-3 steps, you get lost. So you better, the one thing I understood is that the diagonalization you do in matrix P is a trick. So I would say that as the first and foremost contribution. Because this allows you to simplify the computational complexity of the problem.
Right.
If I understood correctly.
Yeah.
And you should say that. That is an easy message to convey. The entire fact that you have this kind of structure, and like in slide, for example, 10, there was, in slide 10 there was, this constraint optimization formulation, which is kind of redundant, because of course you want to maximize the rate subject to power constraints. That's easy to understand. If you just say classic maximum maximization of rate, you don't need to formalize it downwards. Plus, there is this problem with the signomial functions. As you say, the problem is complicated, and you have to justify why it's complicated. I wouldn't say that. I would just say this is a complicated problem. The details are on the paper, because I don't think there is a chance that anybody. I mean, if somebody already knows what an NP-hard signomial problem is, they know already. But I doubt anybody will take a look at the red footnote here. If they say, okay, that's an NP-hard signomial, I don't know, okay, too much. Turn off the brain. I think you should refer them to the paper for them, and you say, okay, the problem is complicated. Thanks to our approximation, we were able to solve it easy. I would say so. I mean, at least for ICC presentation, for a conference presentation where most of the people don't know about constraint optimization. Well, they have heard of constraint optimization, but they don't know it down to this level of detail.
Yeah, I see.
And same is for slide 12. Again, in slide 12 you have this detailed description of the scenario, just too much. I mean, most of the choices there are pretty standard, so you can even put them somewhere in a dedicated slide and just, I mean, you show them and that's it. But the most interesting part is the bottom part, where you show the comparisons, and this I will detail more. Because this, to understand the universal random pilot assignment, the smart pilot assignment, and the pilot power control with brute force search, I mean, they should be shortened, but those are the useful comparison terms.
Yes.
And in the figures, you said exactly what I advised against you to. You have some comments below the figures, which are pointless. I mean, from the figure, you already see that the smart, for example, the smart pilot assignment is better. Of course, if I remember correctly, the brute force search is even better, but it's unfeasible because brute force. So you are, from the figure, you already see that this is better than the state of the art, close to the brute force without the same computational complexity. That's it. You could just put a big figure. The figure is actually very nice.
Yes.
It's perfect. Gives, maybe lines could be thicker, just to be nitpicking, because I bet that the pilot power control with brute force might be hardly visible, depending on the projector.
Yes.
But
The legend overlap with the figure.
yeah, the legend overlap is manageable. I mean, that's not a big problem, provided you see how the curves work. But I think you should just give thicker lines, but the colors are good, the differentiation is kind of understandable, the figures are recognizable, the green is dark enough, and I mean it's decent. But you should do the big figure without comments.
Yeah.
I mean the comments, you can save them for a printout version,
Yeah.
if this is going to be downloaded by somebody and checked it offline. But if you're going to present it, you can say with your voice that your proposed pilot design is good and close to the brute force without having the same computational complexity, better than the alternatives. This is already visible, so you don't need to write it down. It's kind of redundant. It saves space. You can do better with a bigger figure, I think.
Yes.
And that's it. I think, well, other comments are more or less in general. Well, a minor comment is that the title at the bottom is too long,
Yes.
because it goes, it overlaps sort of with the COMSYS logo.
Yes.
You better try to summarize it, because in the end it's, well, joint polishing is a kind of mouthful. So you can put it shorter, like it's your contribution, nobody doubts it. Joint polishing design, blah blah blah, in MIMO.
Yes.
So you can put dots, but still that's minor.
Yeah.
The main problem is that you try to explain what you did, which is very technical. It's actually very good. The topic itself is very interesting. But in ICC conference, there will be 2 people understanding it. You better go for saying,
Eric de Marzet.
yeah. My contribution is I proposed a simplified assignment which just look at the diagonal of the matrix. That's a trick which saves you computational complexity, but works very well if you, I mean, you do the diagonal, but if I understand correctly, you find the correct basis so that the diagonal is efficient enough.
Yes.
So you say just that. That's it. Then if you are interested in knowing more, you read the paper. Because in the 15 minutes, it's probably impossible to explain all of this. That's in a nutshell, all my comments.
Yes, I know about that problem. However, one problem rising from my side that, if I only write something, if I only show, to be honest, if I only show the figure here and with a few words,
Yeah.
and then if my presentation skill is not quite good, and and I also somehow for example, you are as a professor position, therefore you have enough confidence to deal with all problem. However, is my case different? If I become too nervous, maybe I forgot everything. If I understand correctly, your point is you fear that if you just put the figures and you don't remember how to explain them well, you don't feel confident enough, you think people will read all the text. My reply to this is that you should definitely try to explain the figure, because very few people will bother reading the text. Yeah, I see.
If you, it would be better if you feel nervous, you might find some way of memorizing the text or write it down the text, but don't write it on the slide.
Yes.
That would be better. At least, the best thing would be to explain things by heart.
Yeah.
But if you feel that you don't remember all of the path, all the steps to explain the matrix graphical representation,
Yes.
I don't think the solution is to put this text over there, because the matrix looks much prettier from, well, first of all from capturing the tension,
Yes.
and also for explaining things, because certain representation, which are basically the formulas you have in the paper, they, well, look some time to be digested. The graphical representation is much better, but it's too small.
Yeah.
Put like that, it looks like you think, okay, this is worthless, what's important is here in the text, which is actually not true, because the matrix representation gives much more meaning. It's easier to recognize that you find the correct basis and then you diagonalize and everything from the graphical representation, to me at least,
Yes.
which I'm not an expert of I'm not an expert of massive MIMO systems.
Yes.
So, and I guess the same for the average attendee of ICC or any conference. This, I mean, unless this is for a seminar or a workshop in massive MIMO, that would be perfect. But for a general conference, it's definitely best the graphical representation. In your case, you already have it, and it's much better, believe me.
Yes.
Then you better take some notes, and you read notes while presenting it, or you set the PowerPoint in present. Well, that's PDF, but you set a presenter view where you have some side notes that you read if you don't feel confident, that you fear to forget something, but you don't tell the audience. That's why, I mean, it's something for you only. It's your hand out for, I mean, like the instructor notes. It's something don't tell the audience. It's just for yourself. At least that's my advice.
Yes, I will try to improve my presentation. Hope that if you attend ICC, you can see That's a good point. That's a good point. Yes. That's a good point.
Very good point. Okay. Okay, so we have some, the guys at the very back.
Yes.
As I understand, for passive MIMO,
Yes.
when we have the pilot sequences and also the pre-coding or the downlink,
Yeah.
both of these have to be less than the coherence time. Could you just comment, in the sense what I understand is that of course we cannot have the brute force method, but you've used successive approximation, which is also heavy in my opinion. I don't know if you have already considered or if you could comment on how it works with successive approximation. That have you considered what is the ratio or some comparison between the coherence time and the time required for the pilot sequence?
In the downlink, we only, first in the downlink, we only need to use pilots if the network operates in FDD mode, right? In the TDD mode, we don't need to. We only need pilots for uplink training. We don't need for the downlink. And for and come back. Just my comment. Come back with the successive interference, successive approximation method. Yeah, I know that it somehow iteratively solves the problem. Therefore, it will become burdensome if the number of iterations, for example, is go to infinity or with a very large number of iterations. However, in a simulation, we see that the conversions converge quite fast, and only a few iterations. Therefore, computational complexity is not a big problem here, even though we have to iteratively do that. For example, I observed that to use the successive approximation method, we only need around 15 iterations.
So will it work in mobility? This is the question, I guess. If this does work in mobility conditions.
Or just in real scenarios, because already, as per my understanding, the pilot sequences, it's a research program where you have the pilot sequences and pre-coding,
Yeah.
and people are trying to fix this within the coherence time. So this is one step trying to improve the pilot sequences and increasing the complexity, at least from just general perspective.
Yes.
So my question is, I don't know if it still fits into this time. And for example, mobility, or if it's a larger network, or have you considered this or thought about it?
No, I didn't consider. So, yeah. Yes.
Hi, Trinh.
Yeah.
How are you? I have a question about the system model.
Yeah.
The uplink pilots are orthogonal within a single cell, right?
Yes.
Okay, so this means that you address the intercell pilot contamination, but there is no intracell pilot contamination, right?
Yes.
So the uplink pilot length should be at least equal to K.
Yes.
But
It's
less than K times L.
I mean, with the prior work, they only consider the case with the tau p equal to K.
Yeah, I saw it.
Yes.
But there is no pilot contamination
Between the cell, between a cell and only pilot contamination come from other cell. However, our proposed method in the longer version we approve that our proposed method can work with whatever the length of tau p here. I mean, it even though less than K or it's even though less than K multiply L. I mean, it work whatever you want.
Okay. Thank you.
Yes. Thank you.
Okay. Comments, questions? It's done. Okay. Well done. Thanks, Trinh. Who has got the USB? You don't want to use it. You must stick to the rules.